Okay, so let's get started then. So chapter 3 review. So what I did is I went through chapter 3, which is on derivatives for our book, and just copied all the blue boxes, right? So I don't want to go through the details of chapter 3. That's what you guys did in your previous calculus class. But I just wanted to highlight all the important concepts that you guys already learned, and just to kind of quickly review those, and then we'll do the exercises at the end of chapter 3. Okay, so let's just walk through these, make sure we understand what they're saying. So the first one, that the derivative, right, this style of notation is, that's one of the problems with, or one of the obstacles or challenges of calculus, that there's a lot of notation. And there's different ways of expressing the exact same thing. So one of the styles of describing a derivative is with this way, d dx of c, where c represents a constant, right? So the derivative of a constant equals to 0, right? That's what that's saying. Then we get into describing the derivative of the function x, right? So this is where the function, another way of describing this is to say that we have some function, f of x equals to x, and we want to find its derivative. So the derivative of this function equals to 1, right? So that's what this is saying as well. You can also write it in the form of, if we have the function y equals to x, then y prime equals to 1. Right? These are all saying the same thing. The derivative of this function is 1. Good. Feel free to stop me at any moment as I fly through these concepts here. Yeah, questions? Is that a question?
Excuse me?
Yes, was there a question?
I'm not sure, but I don't know if I remember another way of denoting derivatives. Is that with the triangle x? Or am I...
Sure. When you go into the definitions of what is a derivative, we use the notation of a little triangle to represent the change in. So you might have seen something like this, right? Yeah. So this means the change in the x direction, and then we have a little dy, which is the change in the y direction, right? So it's related. It's closely related. You can review chapter 3 to see that slight distinction there. But moving forward, when we denote derivatives, we don't really use that. We use d dx, or we use this little prime notation thing, like this. We'll put a little tick mark if it's a function like this one, or if it's written in this format with a little tick mark there. So these are really the 3 most favorite ways, I think, to describe a derivative.
Awesome.
Good. Okay.
All right.
Okay, I think someone might have their mic on accidentally out there. So remember, by default, just have it off unless you have something to say, and then turn it on for a minute, and then don't forget to turn it back off when you're done. Otherwise, we're going to have a whole lot of ambient noise.
Oh, yes. Sorry about that.
No problem. All right, moving on then. So the constant, if we have a function multiplied by a constant, and we want to find the derivative of the whole thing, then we can kind of ignore the constant, right? We can move it on the outside and just multiply the constant times the derivative of the function, right? That's what this is saying. So real quick example, if we had 3x squared and we wanted to find the derivative with respect to x on this whole thing, d dx like this, well, this is letting us know that we could just ignore that 3 and multiply it by the derivative with respect to x of x squared, right? As long as we have a constant being multiplied by a function, we can bring the constant on the outside and then take the derivative of the function, right? So that's what this is saying. Moving on, in chapter 3, I'm flying through chapter 3, so there's a whole bunch of stuff, insert 4 or 5 pages here and just kind of hitting all the highlights. The power rule, the general version. First you run into a version where n is only positive numbers, and you do that because you can prove it and you can show it and it's easier to work with. But eventually you run into the general version of it, which lets n be any real number. So this is saying the derivative of any function that fits this form, x to the power of n, where n is any real number, is equal to this, right? So this is probably the most famous pattern in calculus. So, for example, if we had the derivative with respect to x on the function x to the 7th power, for example, right? Here the role of n is being played by a 7, right? And so this little pattern says, well, bring that 7 out in front as a factor and multiply it to the power of 7 minus 1. Right? So the derivative with respect to x of x to the 7th power is really 7x to the 6th power. Right? But, so it's a simple little pattern, very famous, but there's a lot of some concepts that need to be understood to understand why that is. And there's some nice proofs that are given in chapter 3. So hopefully you remember that from Calculus 1. If not, it might benefit you to go through chapter 3 a little bit and see if you can refresh your memory on any of that stuff. Okay, but it's a pretty popular pattern, and so this is saying that it's still a valid pattern when n is any real number. So it doesn't have to be just a positive integer the way I did there. It could be any real number. So for example, we can also have the derivative with respect to, let's change the letter, x is used too much. So say dw, about with respect to w, on the function w to the 3.1 power, like that. Well, according to that property, it's going to be 3.1 times w to the power of 2.1. And that multiplication looks weird, so how about that? Good. So we just follow that pattern, and that's how we get the power rule. Good. Any questions? So far we're good? So far we're good? Okay. Then there's the sum and the difference rule, which are identical, except here we have an addition, and here we have a subtraction. So if we have a situation where we have two different functions being added or two different functions being subtracted, and we want the derivative of that sum or the derivative of that difference, then we can take the derivative of each function separately and then add them, right? So the derivative of the sum is equal to the sum of the derivatives, right? The derivative of the difference is equal to the difference of the derivatives. Good, 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 good. So, for example, quick obvious little example here. If we had d dx of x cubed plus, x to the 3rd power like this, then according to this property, what we could do is take the derivative of one of the functions, x squared, find that answer, and add it to the derivative with respect to x of the other function. Good. So now we know this property, we know this from the property above, that's going to be that, plus 3x to the 2nd power, right? We subtract 1 from the exponent. Still pretty easy? Good? Questions, 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 questions? Okay, so that's all good. Then somewhere along chapter 3, you run into this very important property. The derivative with respect to x of the function e to the x is equal to e to the x, right? That's what's important about this number, the number e. Remember, e is an irrational number. E is approximately equal to 2.718, dot, 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 dot. Goes on forever. It never repeats. There's never a pattern. There's never a repeating pattern. It goes on forever, so it's an irrational number. And the reason we care about this number is exactly for this reason. It's the number that satisfies this. The derivative of that function is equal to that function itself. Right? Good, 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 good. Okay, so that's an important property. Moving on, the product rule. So if we have a case where we have a multiplication of two functions and we want to find the derivative of the product, then this is how we can do it. We can find the product of one function times the derivative of the other, so f of x times the derivative of the g function, plus g of x times the derivative of the f of x function. Right? So if you really kind of look at it for a little while, what this is saying is that we just take turns. We take turns finding derivatives, the derivative of one, the derivative of the other, and multiply them, and then add them together. Good, good, good. So, for example, if we had x plus 2 times 3 minus x squared. Let's say we had that multiplication. Here is one function, here's another function, and then we want to find the derivative of the entire thing, ddx of the entire thing. Well, clearly, one thing we could do is just FOIL the whole thing. So let's do it that way, first of all, just to kind of see the comparison of the two. So one thing we could do is FOIL this, multiply this times this times that, this times this times that, and we end up with 3x minus x cubed plus 6 minus 2x squared. Right? This times this gives you 3x minus x cubed plus 6 minus 2x squared. Good. That equals that. And now we know that we can find the derivative of each one of these separately and then add or subtract them. So that's this minus this plus this minus dx of this. Right? Okay, so then the derivative of this one is just going to be equal to 3 minus the derivative of this one is going to be equal to 3x squared plus the derivative of a constant is equal to 0, so put a 0 there, minus the derivative of this one is going to be 4x to the power of 1. So I can simplify this a little bit and say that it's minus 3x squared minus 4x plus 3. Any questions? No, no, no? Okay, so that's doing it one way. We can FOIL it all out and use our previous properties to find it. Or now we can use the product principle. So using the product principle, we do this. ddx of, and we have x plus 2, 3 minus x squared. Okay, so we have a multiplication of two separate functions. We can think of this as one function, f of x, and this is some other function, g of x, right? And they're being multiplied. Two separate functions being multiplied. So the product property says we kind of take turns and then add them together. So this is going to be equal to, and it doesn't matter what the order is when you actually write it down, as long as you keep track of things and don't mess them up. So let's say we skip the first one, x plus 2, just copy it down, times the derivative of the second one, ddx of 3 minus x squared, plus, and now we already skipped the first one, so let's find the derivative with respect to x of the, actually, let me, again, the order doesn't matter, I just want to write it this way because I don't want to make sure that it's clear that it's not in there. So 3 minus x squared times the dx of now the first one, which is x plus 2. Good? Questions, questions, questions? So this is, another way of writing this is this f of x times g prime of x plus g of x times f prime of x. Right? So we have this product, and in the first one, we leave the f of x alone, take the derivative of the second one, plus here we again write the product down and take the derivative of the f1, leave the g1 alone. Right? So we sort of take turns. Now, the order in which you write these, that doesn't matter. Right? So the order in which we write these two things doesn't matter. Usually we like to write the derivative second because if I write it the other way around, then there's potentially some confusion. d dx of 3 minus x squared times x plus 2. Some people might think that this applies to both of them when I'm really trying to say that it only applies to the first one. So then maybe you'd put some parentheses to make sure it's clear that this derivative only applies to this function times that one. So you could do that, but it just looks a little messier, right? So it just makes a little more sense to write them down in this order, so it's super clear that this derivative only applies to this function. Good. Any questions? No. Okay, so now let's keep going. This is going to be x plus 2. The derivative of this function, that's going to be easy. That's just going to be equal to minus 2x. Right? Derivative of a constant, that's 0, minus 2x to the first power, plus 3 minus x squared, and then the derivative of this is just going to be equal to 1. Good. All right, so now I had to distribute. I'm going to distribute this term times this term, this times that, and I'll end up with minus 2x squared minus 4x plus 3 minus x squared. Right? Also distributing this 1 times each of these gets rid of the parentheses. And now if I combine like terms, I end up with minus 3x squared. Right? Combining this one and this one, you get a minus 3x squared, minus 4x plus 3, and aha, we get the exact same answer as we did before. Any questions? So that's, again, another reason why calculus is really hard. There's lots of different ways to do the same thing. So sometimes we have options, and sometimes we have to be pretty clever about which method makes more sense for a particular situation. Okay, any questions? No. Okay, so we have the product rule, then we have the quotient rule, right? So if we have the derivative of a division like this, where we have a function in the numerator, a function in the denominator, then this is equivalent to this whole thing over here, right? Remember the way to remember this is low d high minus high d low over the denominator squared we go. Right? There's nice little songs about that. You want to look them up. Okay, good. And this is all dependent on the value of g of x not equaling to 0, since we always have to keep an eye out for that, right? Don't accidentally divide by 0. Good. Okay, so there's next in chapter 3, they gave you this nice little table to bring it all together and remember all the concepts covered so far. All right, next we got into the chain rule. So the chain rule is originally presented this way, right? So in the chain rule, we are looking at cases where we have a composition of functions. So capital F is defined to be this, F composed with G, right? Which means it's the function g of x plugged into the function f, so that we have a composition of functions like this. And so the derivative will be equal to, the derivative of capital F of x is equal to lowercase f prime g of x times g prime of x. Good. So for example, let's say we had f of x equals to x to the third power, right? What this is saying is that when you give me an input, I'm going to cube it, right? F of input goes in there, then I'm going to cube it. So it could be the number 7. Okay, I input 7, so 7 gets cubed. Okay, that's what it could be. It could be a function on its own. It could be that maybe the input is w squared plus p, Okay, well then w squared plus p gets cubed. That's what the f function does. It's going to cube whatever you input into there. So if in fact we actually have a definition of g of x, well, that's not g of x, is it? Let's see. G of x equals to x plus 5, x squared plus 5, let's say that. Then when we plug that into here, we can have a g of x into here. Right? Instead of writing x squared plus 5, we can just put a g of x in here. And so that's this, gets cubed, which is equivalent to saying that this whole thing is going to get cubed. X squared plus 5. Right, so this is a composition of functions. We could say that this whole thing is capital F. Capital F is made up of the composition F composed with G. Good. And this is describing for us what the derivative will be. If you want the derivative of a capital F function, which is described in this format, then the derivative is going to be equal to the derivative of the outside function, the f, evaluated at g, times the derivative of g. Good, 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 good. So in our case, if I want to find what's the derivative of this capital function, right? This capital function, it's going to be equal to the derivative of the lowercase function evaluated at g of x, and then we got to multiply that by the derivative of g of x. Good. Questions, 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 questions? Continuing on my little example here then. So the derivative of the lowercase f function is equal to 3x squared, right? And the derivative of the g of x function is equal to 2x, 2 to the power of 1, plus 0. I'll put a plus 0 there. So it's just going to be equal to 2x. Good? Okay, so if I want to find the derivative of the capital of f of x function, which is this complicated thing here, right? From here, I can get that capital F, which is made up of that composition, is really equal to x squared plus 5 to the power of 3. And according to this, it means that I can find the derivative of the lowercase function, which is this guy. So that'll be 3 blank squared, right? That's what this is. But that blank is going to be the g of x, evaluated at g of x, times the derivative of the g of x function, which was equal to a 2x. Good. So as a final answer, I would get 3 times x squared plus 5, which is the g function, squared, times a 2x. And then, okay, I lied, one last step. Let's multiply the 2 and the 3 to give us 6x x squared plus 5 to the power of 2. Right? So that's the derivative of this capital function, which is defined to be a composition of these two functions. Okay. Any questions about that?
Just quickly, I have a hard time with a square exponent after plugging into the function, replacing the g of x where you have 3 parentheses g of x squared. I usually apply it to the 3 for some reason, but I just realized it's because it's part of the function, that's why it goes on the outside, not next to the 3, correct? Because I tend to bring down the x next to the 3 for some reason.
Bring down
I don't know why I
x
do that.
next to the 3.
I mean, I bring down the x next to the 3 instead of replacing it with the g of x. So I've been doing that frequently.
Okay. Yeah. I mean,
But like instead of replacing the, what I'm trying to say is instead of replacing the x with the g function, g of x function, I'm bringing it down, which I'm creating an error.
Okay. Okay, I think I know what you're saying. So at this
Yeah.
point right here, when you were finding the derivative of the lowercase function, you just copied this, 3x squared times 2x? Is that what you're saying?
Yes. It seems like that's what I'm doing, yes.
Okay.
Well,
you know, and
you could explain for me not to do that, I guess. It's because the x is getting replaced with a g, correct? Because it's the input.
The x is getting replaced with a g.
From the f prime x equals 3x squared. When it go to the f, capital F prime equals f prime, the x gets eliminated, correct? Because it's being replaced by the g of x information.
It's being replaced by it here. So let me do it. Let me do this. All of this I did here. I did it in a particular kind of convoluted, messy way because I was trying to match it up to this and you know, kind of show how f is the composition of two functions, define the two functions, and also I made it kind of messy. But in practice, we don't usually do all that work there. In practice, we might do this instead. So let's say f is given to be this one, right? It is the same as the one right up here. It's this one. It is the composition of these two functions. But we don't even really have to know the value of f and g. Let's just say that this is given, and we want to know what is f prime of x. Okay, so what we normally do is think, well, if, right, if, in our heads we think, if we had blank, you know, like say a u to the power of 3, the derivative of this with respect to u would be 3u squared, right? So if this was just one single letter to the power of 3, one single letter, then we'd bring down this 3, right? We'd do a 3, and then we'd bring down that letter, and then raise it to the power of 2, right? So that's the thing that goes in here. So that goes there. Now, we weren't asked a case where there was a single letter, so by the chain rule, we still have to find the derivative of this guy. In fact, let me do the substitution part of it. I think that that's a very popular way of doing this. So let's put let u equal to x squared plus 5. So then we can rethink this as a u to the power of 3, right? And now the derivative with respect to u of u cubed equals to 3u squared. So that's good. That makes it easy if we replaced it in terms of u. However, this wasn't in terms of u, so that means that we get to use this property and write it as 3 u squared times, but now because we did the substitution, we gotta also include the derivative with respect to x of the u. Right, where the u is this guy, so we have to introduce an extra term of 2x. So f of x is equal to 3u squared times the derivative with respect to x of x squared plus 5, which then gives me 3u squared times 2x, where the u is that guy. So we end up with 3x, so let's go a little higher, 3x squared plus 5 times 2x. And then we can simplify this and stick it out in front and say it's 6x, x squared plus 5. Oops, these are primes. And that's in fact what this property over there is telling us that we could do. So the original chain rule is given in this format, and this example was, like I said, I was trying to marry it and show exactly how the g and the f and the g prime and the f prime can all be connected to match it up to this thing. But that's not the most popular way of expressing it. So we often get into this kind of a situation where we have the derivative with respect to x of u to the n, And so now if we take the derivative of this, we end up with n u to the n minus 1. So we took the derivative of this with respect to u, but the original question was with respect to x. So according to the chain rule, we just have to multiply it times the derivative of the u with respect to x. Right? We often use the language of the inside function. So you can replace an inside function with a constant, usually we use the letter u, and then treat that function as one single, a function using that little unit, usually the little u, and then when you're done with that derivative, you still have to come back and multiply it times the derivative of the inside function. Good. Okay, hopefully that sounds familiar, and of course you guys all had different teachers. Sure. You guys all had different Calculus 1 teachers, and everybody does this, does things just a little bit different. So if you guys learned it slightly more in a slightly different way, that's perfectly okay. And we're about to, as soon as I finish reviewing this, we're going to go hit the examples from the review section. So there'll be plenty of opportunity to apply these concepts. Good. Okay, next, in Chapter 3, you ran into some other great derivatives, important derivatives. So the derivative with respect to x of a function b to the x, remember b is a constant, is equal to this, b to the x ln x. Right? Ln is the natural log. And the derivative with respect to x of the natural log of x is equal to 1 over x. Right? This is really, really popular in math. You're going to run into this a lot in the applied sciences. So derivative of ln x is equal to 1 over x. And then in a more generic format, the derivative with respect to x of log base b of x is equal to 1 over x ln of b. Notice that in this case, right, ln represents log base e. Come on. Remember that ln of a is the same thing as log base e of a, right? That's what this is. ln is the log base e. So this guy right here, if we replace the b with an e, then we get this. Okay. So if we have log base e of x and follow this little rule, find the derivative with respect to x of this guy, we end up with 1 over x ln of e, right? Just replacing that b with an e, and ln of e equals 1. So this is exactly that, right? It's just a more generic version of it. And we just point this one out because we use it so often that it's nice to remember it this way. Good. Look familiar? Okay, and then we can use the chain rule as part of this. ln of u, right? We want the derivative with respect to x of ln u, assuming that u can be described as a function of x, then we can find its derivative. So the derivative of ln u is 1 over u times, and now we have to multiply by the derivative of the u function with respect to x. Right? So quick little example of if we wanted to find, if we had ln of 3x squared plus 2, say we want that, and we want the derivative with respect to x of this whole thing. Okay, so if this had been just a single letter, ln u, then we know that the derivative is just to take this underneath 1, right? So this is going to be 1 over this part of it, which is 3x squared plus 2, times the derivative of that inside function. So then we'd still have to multiply it this way, d dx of 3x squared plus 2. Good. So our final answer would be 6x over 3x squared plus 2. Good. Questions? Kind of, maybe, kind of. Okay. Next, the derivative with respect to x of ln of the absolute value of x is still equal to 1 over x. We run into that little property from time to time. Then the book gets into some of our trig functions. So the derivative with respect to x of sine x is cosine x. The derivative of cosine x is negative sine x. Derivative of tangent is equal to secant squared. Derivative of cosecant is negative cosecant cotangent. The derivative of secant is secant tangent. And the derivative of cotangent is negative cosecant squared x. Good. Again, I'm just hitting the highlights from chapter 3, so I'm not going to talk too much about why that is. But if you don't remember these guys, go back to chapter 3, and they do a beautiful job of explaining some of these guys. The derivative of sine, why is it cosine, why is this one negative sine. Good, good, good. And then again, I'm not going to go into detail why, but again, the book does a really nice job of explaining some of these guys. So we have the derivatives of inverse trig functions. Derivative with respect to x of sine inverse of x equals to 1 over the square root of 1 minus x squared. I'm not someone, this is a good time to mention it, I have a terrible memory, so I'm not really someone that would expect people to have all of this memorized. Some teachers do, so I don't know, maybe your Calc 1 teacher made you memorize all of this, but I don't think that that's really necessary. So if you have a little cheat sheet on the side that has these kinds of principal derivatives, I think that would be fine. And, you know, of course, in this semester, I have little control over what you have in front of you anyway. But even if this was a regular in-class person-to-person setting, I don't mind having a little cheat sheet of the fundamental derivatives. You know, I'm not gonna ask you on a test, give me the derivative of tan inverse, and then you just copy it. You know, we're gonna get a lot more involved, so I think it's okay to have the fundamental ones. So as you're doing your homework and stuff, I don't think it's a big deal to have these guys, you know, at hand. Good. And then the book finished off with a reminder. I don't know if it's the first time you've seen it, but a little description of how we can find E, right? The definition of E as a limit. You probably covered that somewhere. Well, I mean, yeah. Okay. Any questions on any of these concepts before we do some exercises and apply them? All right, so that was chapter 3 in a nutshell. Super fast, super painful. Let's do some exercises to review those concepts. Okay, so let's do a couple of these guys. I think I said one every other odds, right? So 1 and then skip 3 and then 5 and then skip that and 9, skip that and 13, skip that one, 17, 21, 25, 29, 33, 37, 41, 45, 49, 53, 57, 61, 65, 65, 69, 71, 75, 79, 83, 87, 91, 91, 95, 99, and 103. You can stop there. Okay, and then I said to skip anything you run into that might have a sinh or a cosinh in it, since we're not going to work on that. So see, like here, sinh, number 43, I think number 45 also has a sinh, so hopefully you just skip this one. Okay, so of the ones I highlighted, obviously we don't have time to cover all of them. Let's just do a couple of these. Let's begin with, I'll take some suggestions. How about in the single digits one, starting early on here, 1, 5, or 9. Does anybody have any questions or issues or would like to see me do any one of those three? 5, 1, 5, or 9?
Yeah, I already got stuck on number. I did number 3, which trying it, but you can do number 1 for me.
Sure. Okay, I have a request for number 1. Okay, let's get started there. So, how am I gonna? What can I do? Oh, that's super blurry. Okay. Good enough. At least we can see what it is. So, find the derivative of this thing, and I'm going to copy it again. Sorry that this thing is so blurry. Y equals to x to the second power plus x to the third power raised to the fourth power. Okay, so already we can use our chain rule. Right? If I had just asked you what is the derivative with respect to u of this, well, that's easy, right? That's just going
to the third.
4u to the third power. Okay, so why don't we do a u substitution here? Let u equal to x squared plus x to the third power. Good. So that means that my derivative is going to be equal to the derivative with respect to u, ddu, of this thing, u to the fourth power, times the derivative of u with respect to x of the u function, which is going to be equal to x squared plus x to the third power. Right? So, I can put a finger over this part of it, right? Cover it up, pretend this is one giant u, take the derivative of it, and be done with it. And when you're done with that derivative, then we just have to attach to it the end part of it, which is to take the derivative of that function that you kind of ignored. Good. So moving on here. So this is saying that, next guys, so this means that y prime is going to be equal to 4u to the third power times the derivative with respect to, well, this is bad notation actually. Sorry, this shouldn't be there. It's the derivative of u, this thing is u, with respect to x. Okay, so then this is going to be equal to 2x plus 3x squared. Good. We're almost done, except nobody asked me about u. We need to get rid of that again. So y prime is going to be equal to 4 times x squared plus x cubed to the power of 3 times 2x plus 3x squared. And we're done. Good. Questions, 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 questions? We're good, we're good, we're good. Okay, so let's move back over here. All right, so what about something in the teens? Any questions about one of these guys, 13 or 17? We don't have time to do them all. I do want you guys to try some of these, so let's move on then. How about something in the 20s? 21, 25, 29. Nothing.
Number 25.
25. Let's see. Okay, so I wonder why this thing is so blurry. I'm trying to figure out something I could do with this. All right, 25. All right, well, at least it gets it close enough to be able to figure out what it is and then copy it. 25. Okay, so again, we want to find the derivative with respect to x, right? So the instruction said find y prime, right? And we have this equals to x squared minus y. So we want to use synthetic division in order to solve this. So using synthetic division, what we want to do is take the derivative of this thing. So we want d dx of this side, sine of xy, is equal to d dx of this side so first we're going to take the derivative of this. So the derivative of this, using the chain rule, is going to be equal to cosine of xy times the derivative of the inside function, d dx of the product xy. Good. Equals to, and well, this we can just break it up into two pieces. This is d dx of x squared minus d dx of y. Good. All right, this thing is a product rule, so we got to break it up. This will be cosine of xy times, and then the product rule says we take turns, right? We're going to take the derivative with respect to x. Well, here. Let's do x times the derivative with respect to x of y plus now y times the derivative with respect to x of x. See how we took turns? One of them is a derivative of one function, the other one is a derivative of the other function, and we add them together. Right? That's the product rule. Equals, and then on the other side, well, the derivative with respect to x of x squared is going to be 2x. And the derivative with respect to x of y, well, we don't know what that is, right, since this is a different function. So this is just going to be dy dx. Good. Okay, so here, this is also dy dx. And here, the derivative with respect to x of x is going to be equal to 1. Good. So what we have is cosine of xy times x times dy dx plus y times 1 equals to 2x minus dy dx. Good. And keeping in mind that what we're trying to find is dy dx, right? That's what this is. Questions?
I'm sorry to interrupt. I'm wanting to ask for dy over dx. Is it okay if I put y prime?
Yeah, they both mean the same thing.
Oh, okay, perfect.
Same
Thank
thing.
you.
Good. Be careful not to confuse it with dx dy though. So it's important that y prime is dy dx. right? And
Oh.
this is under the assumption that y is a function of x,
Oh, got it.
right? So this is if y equals to some function of x, right? Like y equals to something in x squared minus 2x cosine of x, whatever. Good. Okay. And then, you know what? When I finish with this, we'll do it in the other notation because it might look a little prettier in the other notation style. Okay, so we want to solve for this guy. So I'm going to distribute this cosine. This applies there. This applies there. And then I'm going to move all the terms that have the derivative of interest, dy dx, on one side. So this is going to be equal to cosine of xy times x times dy dx plus y times cosine of xy equals to 2x minus dy dx. And now if I bring this term over here and move this term over there, I'll end up with cosine of xy x dy dx plus another dy dx is equal to 2x minus y times cosine of xy. Is that clear? All I did is I took this term and moved it over here, and then I took this term and moved it over there. Why did I do that? Well, now I want to factor out these terms, and then eventually I'll divide. So if I factor out the dy dx, we'll end up with dy dx, parentheses, cosine of xy, and there's another x, just to make sure there's no confusing, it doesn't get nobody gets confused about this x here. I'm going to stick it out in front. That way it's x times cosine xy plus 1 equals to 2x minus y cosine xy. Good. And finally, we're ready to find the answer. The dy dx is equal to this divided by this. dy dx is equal to 2x minus y cosine of xy divided by x cosine xy plus 1. Any questions?
No.
So, you know, like I said, notation is a big issue in calculus. There's lots of different ways to express the same thing. Different notations can be used. So let's use the other notation style instead of dy dx. See if people like that better. Let me zoom out a little bit more. Here, okay, so instead of this notation style, what we could have done is followed it up this way. Sine xy is equal to x squared minus y. And so if I just want to use the other notation style, I can say I'm going to take the derivative of both sides. So this was going to be equal to cosine xy times, and then I want to say that this is xy prime, right? So the derivative of the y one plus y, and then the derivative of the x is just going to be equal to 1, so I'll just put a times 1 there, equals to 2x, right, minus y prime. Good. And then here is the y prime we're interested in, right, which is the same as this step over here somewhere. Cosine xy times, and then x times dy dx, plus y times dx or dx, so d dx of x, which is a 1, equals to 2x minus y. So distributing, we end up with cosine xy times xy prime plus y times cosine of xy equals 2x minus y prime. And then moving this term to the left, we end up with cosine xy times x times y prime plus y prime equals to 2x minus y cosine of xy. xy. Good. And then we factor out this y prime, giving you x cosine xy plus 1. And I should make it a bracket instead of a parentheses here. Equals to 2x minus y cosine of xy. And so, as a final step, we can divide both sides and we end up with the exact same answer. So it just depends on which style you're most comfortable with. You get the same result. Good. Any questions on these? Good. So remember, implicit differentiation means that we go through it, and if we run into a function that just has x, right, we take the derivative across, and if we run into a function that has an x, we take the derivative like normal. But if you run into a function that has a y in there, then we assume that the y is a function of x. We can use the chain rule property to find its derivative, and then we just attach the derivative with respect to x of the y. So we attach a y prime because we assume because we assume this exists. Right? That's the implicit part. Make that assumption. So this is, again, reviewing chapter 3. So if you're having trouble with this, there's a whole section called implicit differentiation in chapter 3. All right, good stuff. What else we got? So that one was number 25. How about something in the 30s? 33 or 37? No, we're good with those?
Just, if we have time, can you do 33? Might as well.
33. Okay, so ln of the absolute value of these two. Okay, so let's... Okay, so remember that one of our properties was that if we have ln of the absolute value of x, and we want to find the derivative with respect to x of that, this is equal to 1 over x. Good. And now if we couple it with the chain rule, then this is going to be a really easy answer then. So we have y equals to this function, and we want to find its derivative, so let's use this notation. Y prime is going to be equal to 1 over whatever is in there. So this will be secant 5x plus tangent 5x times, because of the chain rule, right, since it wasn't a simple x here, it was a function, so now we have to multiply it times the derivative with respect to x of that function. Secant 5x plus tangent 5x. Good. Now, we leave this alone. This is going to be equal to this, secant 5x plus tangent 5x times, okay, so we know we can distribute these derivatives. So this is going to be equal to, it's going to be the derivative with respect to x of secant 5x plus the derivative with respect to x of tangent 5x. Good, so we take the derivative of each one separately. Now if this was just a single letter here, secant of the independent variable, and then it matched with this derivative, then it would be a straightforward application of our derivative for it. Which number is this? The derivative of secant is secant tangent, right? So let's go back over here. It's been a while. I forgot some of these things. Derivative of secant is secant tangent. Yeah, see, the derivative of secant is secant tangent, and the derivative of tangent is secant squared. So we want to use these two properties here. So if I had the derivative with respect to w of secant w, the answer is secant w tangent w. That's messy. Secant of w is secant of w times tangent w. Okay, so this guy is useful. And if I had the derivative with respect to w of tangent of w, the answer would be secant squared of w. Right? Okay, so we want to use those two properties here. So this is going to be equal to, the derivative of this is going to be equal to secant of 5x times tangent of 5x. But because I didn't have a single variable here that matched with the derivative, I have to use the chain rule to multiply it times the derivative of the 5x. Plus, the derivative of tangent is going to be equal to secant squared of the 5x. And again, because it wasn't a single letter that matched the derivative of interest here, we have to multiply it times the derivative of the 5x. Right? All of this gets multiplied by this other function that we had over here. Let me zoom out. All of that gets multiplied still by this, right, which was 1 over secant 5x plus tangent 5x. Good. All right, so now the derivative with respect to x of 5x, that's just going to be 5. And the derivative of this, well, that's just going to be 5. Good. So we're ready to write down our final answer. The derivative of the function is going to be equal to, now this is a multiplication, so it's going to be one giant fraction. I'm just going to write it this way. A giant fraction where the denominator has a secant of 5x plus tangent of 5x, and the numerator is going to have a 5 times a secant of 5x times a tangent of 5x plus a 5 times secant squared 5x. Good. Good, 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 good. Okay, now if we factored out a secant and a 5 from here, factor out a 5 and a secant 5x, 5 and a secant of 5x from the numerator, then 5 and secant 5x, we end up with tangent of 5x. plus, and then 5 and a secant 5x, there's going to be one more copy of secant 5x. Oops, not squared. Secant of 5x is what's left in the numerator. All of that gets divided by this secant 5x. Wait, there's an addition, right? So it doesn't really matter in what order I write them. So if you don't mind, I'm just going to switch it around to make it look prettier. I'm just going to switch these two and write it as a tangent of 5x plus a secant of 5x. And now it looks nice and pretty, and I can tell that this whole thing as a unit will cancel with that, right? Not individually because of that addition problem. I can't cancel a tangent 5x and tangent of 5x, but as a little unit, as a little binomial here, this whole thing can cancel with that whole thing, reduces, and we finally arrive at our final answer. The derivative is going to be equal to 5 secant of 5x. Any questions? So we had to draw on several of our properties to find this answer. The derivative of an ln absolute value of x function, right? We had to think about the derivative of a secant function, the derivative of a tangent function, and we had to apply the chain rule several times. Right? We applied it to begin with way over here. When we first applied this, we applied the chain rule. We pretended this was one single letter, one single independent variable, and so its derivative is 1 over that value, right? That's why I did 1 over and copied everything in there, exactly the way it is, times the derivative of that function that we just ignored. And then here, once again, we're going to run into a chain rule. Since when I find the derivative secant, again, I don't have a simple little letter that matches that. If this was just secant of x, then I would just write secant x tangent x. But because it's a more complicated statement, I have to also, once again, do the chain rule. Any questions on this one? No? We're good? We're good? We're good?
Thank you.
Sure. Okay, let's move on to these guys. 41 or 49. We're running low on time, so I'll skip those. Let's move on to something like 53. How is that one? Fine. So it's got a double prime on there. That just means find the second derivative, right? So you find the first derivative, get an answer, and then you find the next derivative. So find the second derivative of the function. That seems like it should be doable, right? Should be okay. 57, find an equation of the tangent to the curve. Well, there's only one like it assigned. I would hate to do it for you. How about if I do 58? It's a hard one, so it does take a little bit of work, but I don't want to take your toy away from you. How about if we do 58? If you're having trouble with 57, to follow 58, you should be able to do it on your own. And what does it say? It says, the instructions, find an equation on a line tangent to the curve at the given point. Should have copied that part of it too. Find an equation of the line tangent. Okay, tangent at the given point. In order to be able to do that, we need to find the derivative of this thing. So how are we going to find the derivative of this guy? Here we go. Okay, so given this function, how do we find the derivative? Well, this is a perfect opportunity to do our quotient rule, right? So the quotient rule says that the derivative of this function is going to be a giant fraction where we have low d high, so the low function, times the derivative of the high function. You got to be careful with the order. Low d high minus high d low over the denominator squared we go. Good. Okay, so now simplifying some of these, this guy up here is going to turn into 2x, and this guy is going to turn into 2x as well. Right? 2x minus 0, 2x plus 0. So this is going to be x squared plus 1 times 2x minus x squared minus 1 times 2x all over x squared plus 1 squared. Good. Just to simplify things a little bit, I'm going to factor out the 2x, since that's easy to factor out from the numerator. And then some stuff will reduce from there. Right? So I'll end up with y prime is equal to 2x, giant bracket, and we'll end up with an x squared plus 1 minus, now be careful that this subtraction applies to both of these terms, so I need to distribute it there and distribute it there. So I'll end up with a minus x squared plus 1 in the numerator. The denominator still has this crazy x plus 1 squared term. Okay, luckily these guys cancel. X squared minus x squared cancel, and then 1 plus 1 becomes 2. So this is just going to become 2x times 2 all over x squared plus 1 squared, or 4x over x squared plus 1 squared. Oops, this is a prime. So there's our derivative function. Good. All right, so putting all that work aside, let me just put it over here and say y prime is equal to 4x over x squared plus 1 squared. Okay, how does that help us, right? The original statement was find the equation on a line tangent to this function at this point, right? So we can visualize what this function is. So just in general, if we have some function, I'm not graphing it, so I'm not sure what it is. So let's just say it does that. And we want to find a point tangent, right? So if we want to find a point that is tangent, there it is. So it would be something like this. So it's like that. So the tangent is going to be a line, right? So the tangent one is going to follow either the y equals mx plus b format, or the y minus y sub g equals to mx minus x sub g, right? Where g is for the given one, right? The given point, if you have a point. Okay, and now what's special about this function? This is a function that gives us the slope of the line's tangent to the function, right? That's the whole purpose of the derivative function. So if we plug in a 0 into here, what's going to happen is it's going to give us the slope of the line tangent at that point. Does that make sense? Good. Okay, so let's go here. So for us, we have 0 comma negative 1. So therefore we have that x is 0 and y equals negative 1. So y prime at 0 is going to be equal to 4 times 0 over 0 squared plus 1 squared, which is equal to 0 over 0 plus 1 squared, which is just going to be equal to 0. So what kind of a line has a slope that's 0? The line tangent at that point has a slope of 0, which means it's going to be completely horizontal. Good, 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 good. And so it'll end up being, right, if we wanna plug it in, we have y minus y given equals to m times x minus x given, right? And here are the 2 points that we have. So this is going to be y minus -1 equals to 0 times x minus 0. So this is just going to become y plus 1 equals 0. So y just equals -1. Any questions about that one? Maybe, sort of, kind of, maybe, sort of, kind of. Since we do have the benefit, so this one's in general, right? I just didn't want to graph it, so don't let this confuse you. This is just in general, what does it mean for something to be tangent? In general. So this isn't the function here, but given some general function f of x, the tangent one means that it looks like this, right? It touches at exactly 1 point, and the equation of the tangent line is going to be a straight line, and lines have one of these 2 forms. Does that make sense? That thing. Good. Questions, questions, questions? As long as we do have the benefit of the internet, let's graph it. So I like to use Desmos a lot. Desmos.com. It's free. Click on there. Go to graphing calculator. And we can graph that equation. Y equals 2, and what was it? Like x squared minus 1 divided by, oops, no, the whole thing in parentheses, and then divided by x squared plus 1. I think that's what it was. X squared minus 1, x squared plus 1. So there it is. So that's what the function looks like. So now it's not hard to see that the line, let's make it a different color. Let's make this black. Now let's make it blue. And now we have the equation of the line that's tangent at the point, remember we wanted the point 0, -1. That's this point right there, right there. Let's make this darker. Projector mode. So here's my function, y equals to x squared minus 1 over x squared plus 1. That's this purple function looking here. And then I have this point right there. And we wanted to find the equation of the line which is tangent at that point. And so I think it's clear to see that -1 is our answer. Let's put it in red. Good. Any questions? And that's because the slope is, 0. Right? Sometimes the book chooses values that are simple so we can kind of build the concepts, but sometimes they're so simple that we end up getting a little more confused, I think, just because 0 and 1 are so often used that it gets a little confusing. How about if I tried to come up with a different one? So I've already answered this question, so don't confuse that. Let's just find a different one. So for example, what about this guy? This one's another one that's going to be easy. right there, if x is equal to 1, we'll put a 1 there and a 1 there, I'll end up with a 0 over 2, which is just going to be 0. So my function is, it's got the point 1 comma 0 there. What about our line tangent there? What's the equation of the line tangent there? Let's find that answer. So instead of 0 comma 1, I'm sorry, 0 comma negative 1, let's work on a different one. Now, find the equation of line tangent to y, to y, y equals to x squared minus 1 over x squared plus 1 at point 1 comma 0, right? Where if I put a 1 here, 1 squared minus 1 is 0, so the whole output is going to be 0. Okay, in order to figure out the equation of the line tangent to this function at this point, we again go back to our function that describes the derivative, right? The derivative function describes the slopes of the line's tangent at various points. So y prime at x equals to 1 is going to be equal to 4 times 1 all over 1 squared plus 1 squared, which will be equal to 4 over, and that's going to be 2 squared, which will be equal to 1. Okay, so my slope is going to be equal to 1 at that point. And so now if I go back to my function, the equation of the line tangent is going to be equal to 1 minus 0 equal to 1x minus 1. Good. And that's where this is the x that I go in there. This is the y that belongs in there. And this is the m. The m is the one that's going in there. Good. So we simplify this, and it's a straightforward simplification here. That's y minus 0 is just y. 1 times that is just going to be x minus 1. So there is the equation of the line that's tangent to our function at the point 1 comma 0. Good. So let's let y equals to x minus 1 in our graph and see what that looks like. Y equals to x minus 1. And you know what? This projection mode is a little too thick. There we go. And let's change it to a red color again. There we go. Done. Good. So right there, this red line there represents the equation that we need. Good. Questions? Let's see, how can I make this more general? So let's say that I make this f of x like that, and then my equation is going to be equal to y, let's see, parentheses, y minus, parentheses, y minus f of x, no, let's make it f of a, making a slider, equal to m, and m is the derivative of the function, so that'll be f prime evaluated at a will give me that slope, parentheses, x minus a, like this. Okay, so see how I've recreated that linear equation? This is y minus y given, right? And this is for any random point. Let me get rid of this guy and that guy. Oh, in fact, let's label a comma f of a. label it. There we go. Okay, so let's get rid of this thing for a second. So here what I have is, whoa, that got crazy pretty quickly. All right, so looks like I don't need to go that far. Let's make this from negative 1.5 to positive 2. Positive 2 by 0.01 terms. There we go. Okay, so see how it's a little slider that's identifying an individual point on my function, right? Where this purple function is this one. Good. Okay, so that little point right there, that little guy right there, is a comma f of a. That's what's being labeled, a comma f of a, where the function f is defined up here, right? This was the original function given. Good, 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 good. Okay, so now what I can do is use my my equation for a line. Remember, it's y minus y subgiven, so a point, the y on a point, which is f of a, equals the slope of the line, which is the derivative of the function f evaluated at a, so f prime of a, times x minus a. Okay, if you get that, great. If not, then don't worry about it. That's not really that important that you are able to type it in here that way. But what this will do, it automatically gives you the tangent line. All right, let's make it red. I like my tangent lines red. Done. Okay, so see, that red line is the tangent line to the purple one, right? At any point along the curvature of the purple, right, there is a line tangent to it, and then that line has a certain slope. The derivative of the purple function will be an equation such that it gives you the slope of all these tangent lines. Right? That's the definition of the derivative of the function. Good. So we just found two special ones. We found this one to begin with. Come on, move. That one. So we found that one. That was the original question in the book. Find the equation of the line tangent to the purple function at the point 0, comma, negative 1. And it's that red line. And that red line is horizontal, it has a slope of 0, and we found that the equation of that line was the equation y equals to negative 1. And then just for fun, I added this extra bonus question. What about this one over here? When we have the point 1, comma, 0, what's the equation of the red line there? And after a little bit of work, we saw that the equation was equal to x minus 1. Good. But nothing special about the point x equals to the point 0, comma, negative 1 or the point 1, comma, 0. It could really be any one of these points, right? So it'd be more fun if I gave you a question like that. Some random decimal number and find the equation of that line. Good. Any questions about any of this? No? 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 Chapter 3 overload yet? Is this all familiar and easy or not so familiar?
On the graph, Professor?
Yeah.
In line item number 6 that you typed in there, how did you get it to display the slider?
You know, when you start typing, so Desmos, when you start typing, it automatically asks you if a new variable you put in there wants to be a slider. So if I start typing something like y equals to w, oops, no, it didn't do that. I thought it was going to ask me.
No, that's what happened to me there.
F of, that's weird. See how I put that one and all of a sudden it asked me for that one? So it's usually pretty intuitive that when I want a slider, it gives it to me. But other than that, if it doesn't automatically appear, then B, what if I wanted B to be a slider? No, I don't want it there. Oh, that's a great question. Maybe we can type slider. Slider. Okay, weird. And then it gives you letters to try as sliders. So I don't know. If it doesn't automatically give it to you, I would type in slider and then put in the letter you want. Put all. Is that going to do? Is that going to give me all? Yeah, it just provides you all kinds of sliders. Letter S, letter L, letter I. I'm sure there's a slicker way of doing it. You know, that's why they invented Google. So figure, you can Google that for Desmos. There must be some slicker way of labeling it so that it gives you the slider you want.
Okay, thank you. That's fine. Thank you.
Anybody else? Questions on this? No. All right, good stuff. Back to our review. Review. Okay, so I did this one, and following that should give you the tools you need to be able to define that one. And same with this one. Find the equation of tangent line and normal line to the curve at the given point. The normal line is the one that's perpendicular. So remember that two lines are perpendicular if their slopes are negative reciprocals. So once you find the slope of the tangent line, all you have to do is flip it upside down and change the sign. Good. Okay, so that's how you can find the slope of it. And at what point on the curve is y equal to sine x cosine is tangent line horizontal? Okay, that should be easy, right? Number 65. At what point on this curvature, so this is some equation, some function, at what point does the tangent line, is the tangent line horizontal? So when is the slope of the tangent line equal to 0 is another way of phrasing the exact same question, right? That's what they're asking you for. So all we have to do is take its derivative and set it equal to 0 and figure out when that is. Good. I think that should be okay. Try that out. 69. All these are fun questions. So 69, they ask you to evaluate several of these derivatives. So if f of x, sorry, s of x, p of x are defined this way, find the derivatives. And they're also defined up here. Right? So you just have to follow the instructions for situations like this. So we have the product rule, we have the difference quotient, we have a chain rule situation here. So you just have to apply those properties, and then right up here we have all the relevant function values that we need. I'm a little sad that 70 did not land as one of the target ones, and it's one of my favorite questions. So let's do 70. 69 and 70 are very similar, except in 69 they just gave you the values of the functions and the derivatives, whereas in 70 you have to figure that out based on this little graph here, right? So this is a beautiful test question, one of my favorite questions ever. Hint, 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 hint. So let's do that one. Okay, so if f and g are the functions, okay, so we have the f function here described in red, and we have the g function described in blue, okay? So I've shown let p of x equal to the product of f of x and g of x. Let q of x be the division, the ratio of f of x divided by g of x. And let c of x be the composition of f of x composed with g of x. Find p prime of 2, okay, so part A involves p, right? So p of x is equal to f of x times g of x. That's a product, right? And so they ask us for part A, they ask us for p prime. So p prime of x, we're going to have to follow the product rule, which remember, it's to take turns. It's going to be f of x times g prime of x plus f prime of x times g of x. Good. And the order in which you do it doesn't matter. You just have to make sure you do them, you take turns and you do them once each. Good. So this is what they want, and then they want you to evaluate that at 2. Find p prime of 2. So p prime of 2 is going to be equal to f of 2 times g prime of 2 plus f prime of 2 times g of 2. Okay, so now these are really easy. F of 2 and g of 2. Well, here's 2 right there in my graph. So f of 2 and g of 2 are just these results. Right? Moving up is this one. 1, 2, 3, 4. So from my graph, I can tell that g of 2, that's going to be a 4. Okay. And f of 2, that's going to be a 1. Good. Okay, these are a little trickier. Still focusing on my graph here. Finding g prime of 2. So g of 2 is 4, right? The value of the function at x equals to 2 is a 4. But g prime at 2 refers to the slope of the line tangent at that point. Now it's a straight line at that point, so its tangent line is going to be equal to the actual function. So g prime of 2 is just equal to the slope of the line at this point. And what we could do is we can just count squares. Right, we can just kind of think about this little triangle right here and count squares. There's 2 squares that way, there's 1 square this way, 2 over 1. The slope is 2. Okay. 2 over 1 for g prime of 2. Good. And also noting that it's a positive slope. A little stick person walking from left to right, the way we read, would be going uphill. So therefore it's got a positive slope. Okay, now finding f of 2, that's this little guy right there. Again, we can do a little triangle, and it goes down by 1 and across by 1. This is 1 over 1, it's just 1. But it's got a negative slope because a little stick person walking from left to right, the way we read, would be going downhill. So it's got a negative slope. So this guy is negative 1 over 1. Good, so piecing it all together, g prime of 2 is going to be equal to 1 times 2 plus negative 1 times 4, or g prime of 2, equals to 2 minus 4. And so p prime of 2 equals to negative 2. Questions? Fun problem, right? The answer is yes. Good, good. Okay, let's do part B. Part B says, let's go over here. Part B now has q of x is equal to f of x over g of x, and we know from our quotient rule that that must mean that this is going to be low d high minus high d low over the denominator squared we go. Good. And we want to evaluate all that at 2. So, oops, I shouldn't have done that. That looks ugly. Sorry. This is the function. I shouldn't say that that equals this whole thing. That's not true. We want to say that the derivative of this function equals that whole thing. Low f prime minus f of x g prime of x all over g of x squared. Good. Okay, so now if we evaluate it with a 2, then q prime of 2 equals to g of 2 times f prime of 2 minus f of 2 times g prime of 2 all over g of 2 squared. That looks ugly. Of 2. Good. Well, we already found all of these things. The g of 2, we said g of 2 was a 4. So this is going to be a 4. The f prime of 2 was equal to -1. The f of 2 was equal to +1. G prime of 2 was equal to +2. And g of 2 is equal to 4. Okay. So we can plug all that in and get that q prime of 2 is equal to 4 times -1 minus 1 times 2 divided by 4 squared, which gives me -4 minus 2 over 16, which will be -6 over 16, which reduces into -3/8. Good. Questions? Let me write it over here. So then q of 2 would then equal to -3/8 as our final answer. Questions? Okay, finally, c of x is equal to f composed with g. Right, c of x is equal to f composed with g of x. Right, this is f composed with g, evaluated at x, same thing. And so if we wanted to find the derivative of this function, that's equal to the derivative of the f function evaluated at g times the derivative of this function. Okay. So we already saw that the derivative, we're interested in g prime at 2 again, right? Yep, c prime of 2. So now c prime of 2 is going to be f prime of g of 2 times g prime of 2. Good. So we need to know what is g of 2 and what is g prime of 2. We already have those. G of 2 was a 4, and g prime of at 2 was a +2. Okay, so then this is going to be f prime of g of 2, which is a 4, times g prime of 2, which is a 2. And now we need this. What is the slope of the line tangent to the f function at 4? Right, so this is a new one now. We've got to go back up to our function and figure out what is the slope of the line of the function f at x equals to 4. So let's zoom into here. So at 4, this is 3, this is 4. So I'm interested in that. And I'm not interested in the value of the function at 4, right? F of 4 equals to 3, but that's not what I want. I want the tangent, the derivative there, right? So I want the derivative of f at 4, which is equivalent to the slope of the line tangent. And because it's a straight line, the tangent is equal to the function. So once again, we can just create a little triangle here and count squares. And we end up with 3 squares this way, 1 square that way. Oh, okay. Well, it's unfortunate that in this case they both equal to 3, but for different reasons. Good. So that is going to be a 3. Coming back down here. This is going to be 3 times 2. So my final answer, c prime of 2, c prime of 2, c prime valued at 2 equals 6. Questions? Any questions, any questions, any questions? We're all good? Okay, good. Back to our questions. All right, so we were at 70. Find f prime in terms of g. I think, this is really the same kind of things. So product rule, get the product rule here. Find h prime in terms of f prime and g prime. I think you can do those. At what point is this curvature tangent to the horizontal? Is the tangent horizontal? So find the derivative of this function and then figure out when it equals to 0. Oh, that's a good one. I didn't end up giving you too many of these things, so I don't want to take your toys away, but I want to do a couple of these. Let's look at 100. That's a classic example that will also help you answer number 99. So let's look at this one. Number 100. Okay, a water skier skis over a ramp shown in the figure at a speed of 30 feet per second. How fast is she rising as she leaves the ramp? Okay, so classic question that's going to lead to something that looks like this. So we're interested in this guy. Okay, so we have some sort of a triangle that looks like this. Assuming that we put this on the origin, right? If we can put the origin wherever we want, wherever it's most convenient. So I can put it there and put it there. That's supposed to be on there. So that's the x-axis, the y-axis. So it makes it nice and convenient that that would be 0, 0. And so this distance here would be some value x along the x-axis. That's convenient. And then we'd call this some value y along the y-axis. Good. And then we can call this h for the hypotenuse. Of course, it creates a right triangle. So h is a popular variable to use here. We can also, yeah, let's use h to represent that distance along here, right? And so, of course, we know that Pythagorean theorem applies that x squared plus y squared equals to h squared. Good. Okay, so now we can take derivatives now. Let's take derivatives with respect to x and see what we have. Now, we do have a particular point. We do have a particular point here, so let's redraw this. But at some other point, right, kind of as you go along here, at some other random point, right, as this a value is kind of increasing that way toward 15, there is some y value there, right? So the height starts off at 0, and the height is getting bigger and bigger and bigger and bigger and bigger, and then at this point over here, we reach a height of 4. Right? So their actual height, their exact height at this point is a 4. But this question was asking us how fast is she rising, not what is her height, but what is the speed of her height, right? So we want the speed of y. That's what this is asking us. Correct, correct, correct. So this is some distance from here to here. Oops. Some distance as she's traveling across there. So let's make that a z. The entire thing is d, or h. I used h. The entire thing is h. But now, you know, if you can kind of imagine this as a little variable that slides left and right, then, you know, at this point we have a really small triangle, and as it gets bigger and bigger and bigger, eventually this green triangle in here, eventually this green triangle will be equal to the big black triangle, right? But for the moment, it's just equal to this guy here. So in terms of the little triangle, then if this is 0, then from here to there will be a. From here to here will be a distance of a. And then because this is sort of fixed, then the distance from here to there, that distance is 15 on the ramp. Good. Notice that the green triangle and the black triangle are similar triangles. They both share this angle, right? They're both 90-degree angles. And they both share this corner angle, right? So they both have two angles in common, identical angle, identical angle. Therefore, that guarantees that this top angle up here, I don't know, what do we want to call it, purple, that guarantees that they must also share this one. So they have three identical interior angles. They're similar triangles. And so because they are similar triangles, then we can state that y over z, right, this over this is equivalent to this over that. Good. Good, 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 good. Good, 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 good. Where h is a fixed number, right? H is the fixed number where we have this giant triangle where this is 5, this is 15. So we have, following this thing here, we have that x is 15 squared plus 4 squared must be equal to h squared. So this is 225 plus 16 equals to h squared, or 241 equals to h squared, or h equals positive root 241. Good. So this is just some number. This is just going to be y over z is equal to 4 over root of 241. Any questions so far? No. No, 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 no. Okay, so if we multiply both sides by z, we end up with an equation for y. Y equals to this constant 4 over 241 times z. Almost there. We wanted to find the rate of change of y. So let's find d dt of the left-hand side. Oops. Let's find d dt of the right-hand side. And so we get that dy dt, the speed at which y is changing, right? T is time. So if you want to know the speed of something, then you got to take its derivative with respect to time. So the way that y is changing with respect to time is the speed the y is changing is equal to, and now this is a constant, we can just pull it out, 4 over 241 times dz dt. So the dz dt is the way that the speed of the z, right? This is changing this way. The speed of the z as the a goes from left to right and the green triangle changes, the hypotenuse of that green triangle is going to change. And so it has a certain velocity associated with it, right? The speed of the z. But that's exactly what they've given you here. The water skis over a ramp shown in the figure at a speed of 30 feet per second. As this skier is traveling across this ramp, they are traveling at a speed of 30 feet per second. Good. So right when they hit the ramp down here, they're traveling at 30 feet per second. All the way across, they're traveling at a speed of 30 feet per second. Right when they leave here, they're leaving at a speed of 30 feet per second, right at that point. What we're interested in is this height over here. How is the height changing given the rest of those conditions? Good. So this is 30 feet per second. So we just put a 30 in there. dy dt would be equal to 4 over root 241 times 30. dz dt equals to 30 feet per second. Right? And we keep the same units, so my result is going to be that dy dt, the speed of the height is going to be 120 divided by the square root of 241. Right? And this is still in feet per second. Any questions? Questions? No? All right. Let's see what else we got. So this is a nice classic example that will help you with this one. A balloon is rising at a constant speed of 5 feet per second. The boy is cycling along a straight road at a speed of 15 feet per second. When he pauses under the balloon, when he passes under the balloon, it is 45 feet above him. How fast is the distance between the boy and the balloon increasing 3 seconds later? There was an image of this. There isn't. So for number 99, you can draw it this way. We have something like this. So you can think of the balloon here. Here is the balloon, and it's rising. Right, so this is the height of the balloon is this, and it's on its way up. And then the little boy is cycling down here. So cycling thing, I don't know, whatever. So let's say he's going that way. And then they give you some data points, right? So we can consider this the 0 axis point. So we can consider this distance here as he's traveling to be traveling along this distance here, along the x-axis, to be a distance of x, right? So some point later, he's at this point over here. So 3 seconds later, the little boy is over here, whatever, something like that. And so we're looking at this distance between them, right? This h value, z value, whatever you want to call it. So we call it h. Good. And we have some value y that represents the height of the balloon. And they've given us some speeds. A balloon is rising at a constant speed of 5 feet per second. That means they've given us dy dt. The speed of the balloon is 5. Good. The boy is cycling on a straight road at a speed of 15 feet per second. That means they've given us dx dt. Dx dt equals to 15 feet per second, right? Make sure that all the units match. When he passes under the, when he passes under the balloon, it was exactly 45 feet above him. So at time equals to 0, the balloon is at 45 feet above, right? And the x is at 0 because he's passing underneath it. Okay. And then they're asking about 3 seconds later. At t equals to 3 seconds later, well, the balloon is traveling at 5 feet per second. 3 seconds later, the balloon is going to be at 45 plus 3 times 5, right? Which equals to 45 plus 15, or y equals to 60. Good. And what about the boy? Well, he starts off at 0. He's traveling at 15 feet per second at t equals to 3. X is going to be equal to 15 times 3, which is 45. Good. Questions? So we end up with the equation y squared plus x squared equals to h squared. Good. And we want to find the speed, how fast is the distance between the boy and the balloon increasing. So we want dh dt. So let's find d dt of the left-hand side and d dt of the right-hand side. Too big, let's zoom out a little bit. Okay, so this is going to be equal to 2y times dy dt plus 2x times dx dt equals to 2h times dh dt. Good. So at 3 seconds, so we want to solve for this. dh dt is what they asked us to find. So that means that dh dt, well, first of all, I can divide 2 by everything, right? Divide this side by 2, divide this side by 2. All the 2's cancel. So that simplifies life just a little bit. And so it's this whole thing divided by h, or multiplied by 1 over h. So dh dt is going to be equal to 1 over h times, and then it's going to be y times dy dt plus x times dx dt. Is that okay? I just multiplied both sides by 1 over h, and I just flipped it around a little bit. So I'm just going to check off everything that I have. Dy dt, that's the speed of the balloon. Yeah, dy dt was a 5. I know that one. The y, right, this is when t equals to 3. This is when t equals to 3. Y, we said y was equal to 60. So I have that one. I have that one. X is going to be 45. I have that one. Dx dt, that's this one. We have that one. That's the speed of the boy. So we have all of those. The only one that's missing is h, and h we can get from this little relationship. So again, at that particular point, when x equals to, when t equals to 3, we have that this side is going to be 60, and this side is 45, so we have h. So h squared equals to 60 squared plus 45 squared. So h equals to the square root, the positive square root of 60 squared plus 45 squared. Good. So if we just punch that into our calculator, what do we get? We get 60 to the power of 2 over plus 45 to the power of 2. Enter. We get that. And we want the square root of that whole thing. So the square root of 5625, 75. So this is going to be 75. So now I have everything I need. I didn't mean to go all the way through. I was just going to stop somewhere, but I couldn't help myself. This was too much fun. 1 over 75. The y is, where did the y go? The y is 60 times dy dt. Dy dt was 5. Plus x was 45, and then dx dt is 15. Good. So you can just punch that all into your calculator and get an answer. Hopefully the answer is 13, since that's the answer I'm getting. A second. Good. Any questions? This would make a great test question, right? Who wouldn't love this on a test? Everybody would love this. Any questions? Any questions? Any questions? Any questions?
Quick question.
Yeah.
dxdt was given. Don't remember.
Yes, that's
Well, we got the dxdt.
Mm-hmm. Here, let's read the question again, and that's really important to be able to understand those guys. So the question said, a balloon is rising at a constant speed of 5 feet per second. So based on I just chose the letter y to represent the vertical distance. So y is a distance, but dy dt is the speed at which that distance is changing. So based on that, I get that dy dt is 5 feet per second. And then for the little boy, I just chose to let x represent the distance in this direction that he has traveled. So x is a distance traveled. Therefore, dx dt is the speed at which that variable is changing. And again, right in here, it says a boy is cycling along a straight road at a speed of 15 feet per second. That's how I get that dx dt is 15. And I just stripped away the units, and that's okay as long as you're clear that all the units match. Otherwise, you're going to have to do a unit conversion. Here it was feet per second, feet, and then seconds. So all the units matched. So I just stripped away the units for the purpose, for the math. And then at the end, you had to come back and slap them on. Good. Any other questions?
Yeah, thank you.
Sure. No other questions? No other questions? Okay, that's a pretty good review and refresher of Chapter 3. So I'm going to stop there now. For now, you should make sure you complete the other ones that I didn't do for the review. Make sure you understand the ones I did. So, just because I did it and you see that the answer is 13, that's not good enough. You really got to make sure you understand it, follow through every little step, and make sure it makes sense to you. Because, the questions on the exam are going to be similar to this, but not identical. So maybe I have, instead of a balloon rising and a little boy traveling underneath it, it might be, something about two boats that are traveling and they make this sort of triangle shape as they travel away from each other. One boat is traveling north, another boat is traveling east. And, they might give you the speed of the boats, they might give you the distances, they might ask about the speed at which they are traveling away from each other, that kind of thing. So very similar. It all comes down to forming some sort of triangle and then distinguishing between the distances and then the speeds at which those distances are changing. Good. So make sure you study this and you have a good sense of it. Next week, Tuesday, we're going to continue with review of Chapter 5, which is integrals. So again, if you want to move forward, don't wait for me. Jump over to Chapter 5. Hopefully that'll be a nice, easy review for you, since that's probably where you stopped your Calc 1 class. So integrals, and we're going to be looking or doing the examples at the end of Chapter 5. Good. And then after that, we'll get started with new material and jump over to 7.1. Any questions before we sign off? No, we're good? All right, and have a fantastic weekend, full of math, I hope. Stay safe.
Thank you, Professor. Have a good day.
Professor. Thank you.
Yeah.
Professor,
Yes.
this is Wendy Sparrow. I am having trouble